associate professor at the University of New Hampshire, and he is an expert on computational astrophysics, including binary neutron star and black hole neutron star mergers. Francois, you have 45 minutes, and I'll let you know when you have 5 minutes left before the questions. And you can start whenever you are ready.
Okay, can you hear me all right?
Yes, I can hear you, and I can see the slides.
All right, great. Thank you, and thank you for inviting me to speak with you today. I think you've already heard a fair amount about the state of simulations in binary neutron star and black hole neutron star from David Stokes, of course, just now, and presumably this morning from Carlos and Peter. But I apologize, I didn't wake up at 4 a.m. to actually see those talks. So if I repeat anything they said, sorry about that. For this talk, I was asked to mostly focus on one specific aspect of the modeling of neutron star mergers, and that's the role of the treatment of neutrinos, transport, and neutrino physics in these simulations. So for most of the talk, I'm going to focus on the transport problem, the different algorithms that we have at our disposal, and where we think they can be trusted, or how we think they can be trusted at the moment. But then towards the end of the talk, I'll focus more on which physics is already implemented and which physics is missing in the simulations. And I think that David just already alluded to that in his talk, is that, and I would agree with that right now, is that at the moment it's quite likely that the missing physics in simulations is a more important source of error than the neutrino transport scheme itself, at least when using the best transport schemes available today. But we'll get to that towards the end of the talk. As a quick reminder of the overall physical processes that we are trying to capture here in neutrino transport, where neutrinos matter in simulations. Of course, the first order, the main role of neutrinos in merger simulations is as the main source of cooling of both the neutron star remnant, if there is one, and the accretion disk surrounding the neutron star or black hole, as photons are fully trapped in these high densities. So the main radiative cooling comes from neutrino emission. I would say that the main transport schemes that we have at our disposal at the moment are probably actually pretty good at capturing the overall effect of cooling in simulations. The second and maybe more important aspect of the role of neutrinos, and where neutrino transport becomes more important, is that neutrino matter interactions are the main driver of composition changes in the matter inside neutron star remnant, but also, of course, the outflows. And by composition here, I mean mostly the relative number of neutrons and protons. And we know that the relative number of neutrons and protons is one of the main determinants of the outcome of nucleosynthesis in the matter being ejected in these mergers. And thus, it's important to understand production of heavy elements, but also to understand the properties of kilonovae and try to map the properties of those kilonovae to the properties of binaries, as David already discussed. You can see a rough, you can get a rough idea of the effect of those neutrinos on the plot on the right. This is the kind of plot that I show a lot in this talk. It's a vertical slice through a neutron star merger remnant. The different lines, white lines here, show density contours. In this case, at 10 to the 13, 12, and 11 gram per cc. And the colors here show the electron fraction or proton fraction. In these simulations, they're the same. And you can see, of course, that the central object is very neutron rich, as expected for a neutron star, electron fraction of 0.05 or so. But then the surrounding accretion disk has already been processed a lot by neutrino emission and absorption, and has electron fraction of maybe 0.1 to 0.25 already. And then the matter that is being ejected along the edges of the disk and in the polar regions can go to even higher electron fraction through neutrino emission and absorption. Anywhere between 0.2, 0.25 to even in some simulations up to 0.5. So that's one of the main role of neutrinos. And as David already showed in his talk, depending on the transport scheme you are using, you might get very different answers for what the electron fraction of your ejector is, so which is of course important for us for modeling observable. Beyond that, we also expect neutrino and antineutrino annihilation in the polar regions above and below the remnants to play an important role in possibly clearing these regions of matter and possibly helping the formation of jets, probably magnetically driven jets. neutrinos being absorbed both close to the surface of the neutron star and in the lower density regions at the edge of the disk, and also help drive winds. Also, for strong magnetic fields, we expect magnetically driven winds to be generally stronger. And finally, slightly out of equilibrium neutrinos in dense regions can play the role of viscosity in the post-merger remnant, especially for the first few milliseconds post-merger when some of the matter is still relatively cool. And that is also a potential impact of neutrinos in these simulations that can impact the collapse times, for example, of these remnants. Okay. Now, going into more details, what is the actual physics that we would like to have in these simulations? What are the reactions we would like to implement? I try to separate them here depending on the kind of process that we are considering and how difficult it is to implement them in simulations. The first group, which is probably the most important in terms of matching observables, are charge current reactions, which are all the reactions are responsible for changing neutrons into protons or vice versa. The ones that are included in nearly all simulations are the first and third, so electron and positron capture, as well as capture of electron neutrinos and antineutrinos onto nucleons. These are the dominant source of electron-type neutrinos in most regions, and they are the main driver of changes of proton fraction in your system in most simulations as well. So these are included in nearly all simulations. There is also charge current reactions with muon, which in most existing simulations are not included or not included self-consistently because most simulations do not keep track of the muon fraction, out of equilibrium muon fraction in the remnant. But there were recent simulations by Harry and Zhu that actually included that and showed that at least in the early post-merger evolution for a few milliseconds, these can play an important role also in cooling the system and in changing the composition of the remnant. And I'll show some results from their simulations later in the talk. But this requires evolving, in addition of the electron fraction, the muon fraction, and keep track of two different compositions in your simulations, which most codes are not currently equipped to do at the moment. The second broad group of interactions are scattering interactions. There are two subclasses, I would say. There are quasi-elastic interactions, which are usually treated as elastic, so the neutrino energy does not change, and isotropic, even though they are not exactly isotropic either. Those are scattering onto protons, neutrons, and very subdominantly nuclei. And these are important in setting the diffusion rate of neutrinos through your system, especially for the species of neutrinos for which there are regions where the scattering opacity is large, but the absorption opacity, so the charge current reactions and pair processes are weak. And then for those neutrino species, scattering becomes a very important effect in setting how fast neutrinos can escape your system. This is specifically expected for muon and tau neutrinos, less for electron-type neutrinos. And then there's inelastic scattering, so where the neutrino energy changes significantly, and also generally scattering that is very anisotropic. That is a lot harder to treat in simulations because in theory, to treat those properly, we have to know the distribution function of neutrinos. And we also need an energy-dependent scheme, of course. And so those are the scattering on electrons mainly. And at the moment, they have not been included in full 3D merger simulations, but we think that it could be important for thermalizing neutrinos, especially those muon and tau neutrinos, for which there are large regions where scattering on electron could thermalize the neutrinos, but other reactions that can thermalize neutrinos, the charge current reactions, the pair processes, are not active. So we expect that these could be also important, but they are not included at the moment. Pair processes, so neutrino-antineutrino annihilation into positron-electron pair, for example, or nucleon-nucleon Bremsstrahlung, or electron-positron annihilation. Those are usually included approximately for the heavy lepton neutrinos, because for most of the evolution of the system, they are going to be this dominant source of muon and tau neutrinos, so we need to include them just to get even the cooling of the system properly. But they are only done approximately because, again, because there is two neutrinos involved, if we want to calculate those rates, we need to know the distribution function of neutrinos, a function of both energy and relative direction of the two neutrinos. And usually we don't have that information in simulations, so we can only treat these reactions approximately. But they are expected to be very important for the thermal emission of muon and tau neutrinos. And then, as David was mentioning at the end of his talk, there is flavor conversion. We know that neutrinos emitted as an electron, muon, or tau neutrino are not going to remain that way. As they propagate through a system, they become a superposition, quantum superposition of all three flavors. And the standard, solar neutrino oscillations that we are used to occur on a relatively long time scale, much longer than the evolution of the merger remnant. But there are instabilities at play in the neutron star merger context that can make these flavor conversions fast enough to matter in mergers. So that's things like the fast flavor instability, the collisional instability, maybe the neutrino matter resonance. And this is important because, of course, if you charge some of your electron neutrinos into muon and tau neutrinos, you're going to get less absorption of electron neutrinos in the outflows, and that can change the composition of the outflows. So current simulations generally only include a subset of these reactions. As I said, they nearly all include the electron charge current reactions and the elastic scattering and some treatment of pairs for the muon and tau neutrinos. Everything else tends to be either approximate or not included in the majority of simulations. In addition, there can be significant approximations made in the rate calculations that I'll come back to later on. So the difficulty here in including these neutrino transporting simulations are at least twofold. One is the high dimensionality of the system. We know that Boltzmann's equation, requires us to evolve the distribution function of neutrino six-dimensional function of time. So the distribution function depends on position and momentum of the neutrinos. So that high dimensionality is going to make it very hard, for example, to discretize your distribution function on the grid. In addition, the interaction rate, the source terms in your evolution equations can be very stiff. The neutrino matter interactions can be very fast, and that can make it difficult to treat them in a stable manner in numerical simulations. And the calculation of the reaction rates themselves can be very complicated and require detailed knowledge of the distribution function of neutrinos. And to add to the complexity of the high dimensional problem here, the distribution function of neutrino is very inhomogeneous, both in space and momentum space. And so that makes any discretization of the system very, very difficult to handle. You need basically adaptivity in your discretization if you want to discretize your system of equation. All right, so as a result, most simulations to date use some approximate treatment of neutrino transport. The original neutrino transport methods were just leakage schemes, so some prescriptions for the amount, local prescription for the amount of energy lost and lepton number lost to neutrino emission based on estimates of the emission rate and diffusion rate of neutrinos from a specific point. And this can give you an order of magnitude estimate of what happens. But in the merger context, they usually do not include any reabsorption of neutrinos, and they are very bad at predicting the composition of the outflows. The next best thing, and the one that is most commonly used, I think, in modern codes, is what we call moment schemes. So there we are going to evolve moment of the distribution function of neutrinos, such as the energy density of neutrinos, shown here, the flux density of neutrinos. So these are effectively making the neutrino transport equation very similar to the fluid equation, where we also evolve the energy density, the flux density, and the baryon number density. While in the moment scheme, we evolve the energy density, the flux density, and in some simulations also the number density of neutrino, actually, because to have some information about their energy. So this is very convenient for those of us who are used to evolve the relativistic fluid equations, because it's basically the same equations with a few additional tricks. The problem, of course, is that when you actually write the evolution equations, and I wrote them in very simplified manner here, the GI equations are much more complex. But the general idea is that when you have these equations, the evolution equation for the flux includes the higher moments, the pressure tensor, and we don't know the pressure tensor. In the fluid equations, we can get them from statistical mechanics. We can derive what the pressure tensor is, at least if we know the equation of state, which we don't. But we can at least make a decent approximation. In the case of neutrinos, because they are out of equilibrium, we have to make a guess, an informed guess. Generally, what we do is that in dense region, we assume relativistic particles in equilibrium with the fluid, which is a pretty good approximation. But in low density regions, we effectively make an estimate which assumes that all neutrinos are moving in the same direction, which is definitely not true above a merger remnant. And in the semi-transparent region in between those two extremes, we interpolate between the two in a way that is also inaccurate. So as a result, moment schemes are going to be pretty good at capturing what happens in very dense regions where your closure is actually good, but potentially less reliable in the lower density region and semi-transparent regime, where we are effectively using approximate equations. And one of the issues here, of course, is not necessarily that the errors are large. We don't know. The problem is that we don't know what the errors are. We can't demonstrate what our errors are because we cannot make a convergence test and measure error bars. We are converging to the wrong answer. A second issue is that as implemented in current merger simulations, moment schemes use energy integrated moments. So we integrate over neutrino energy. And so we lose the spectral information. We lose the information about the spectrum of neutrinos. And so we need a separate closure, effectively, for the energy spectrum of neutrinos. And we know that neutrino matter interaction rates are very sensitive to the energy of neutrinos. And so potentially these interaction rates are going to be impacted by inaccurate assumption about the energy spectrum of neutrinos. And the last issue is that the source term here, as already mentioned, are very stiff. And so we need to treat them implicitly. And a lot of the early simulations, including our own, did that in a way that was approximate. And that was more recently improved by David's group and implemented in many other simulations. But treating those implicit source terms properly is important to actually get a correct behavior in dense regions. To give you an idea of what can happen when each of these problem is not treated properly, on the left I show you a very famous example of the problem with the pressure closure, where if you have two beams of neutrinos trying to cross each other, normally, what should happen is what is on the right part of the plot here, they pass through each other. But what happens actually with the standard closure we are using is that they collide and merge into one beam. And this is seen, for example, in the polar regions above neutron star merger remnant, where we get a higher density of neutrinos because neutrinos coming from different regions of the disk collide and merge into one beam of neutrino. This is not specifically an issue with the moment scheme. It's an issue with the closure we are choosing. But we don't have a better closure than the one we are using here on the left at the moment, so that's what we are currently doing. On the right, you can see one of the effects of approximate energy closures. On the other hand, this is the electron fraction of the outflows for both equatorial neutrinos in blue and equatorial outflows in blue and polar outflows in green. The equatorial outflows are not very impacted by neutrino emission and absorption, so it doesn't really matter much. But the polar neutrinos, depending on the energy closure you use, you can get very large difference in the electron fraction, much larger than you would want if you wanted to model Kilinovi, for example. So this can be an important effect here. And then in terms of the treatment of the implicit source terms, this is a plot from David's paper, which shows you the evolution of basically a pulse of neutrinos moving through a high scattering region. The correct answer is the red curve. The two-moment scheme with all of the source term treated properly implicitly gives you the blue curve, which is of course in very good agreement. But some of the older methods that were used, for example, in our code, can lead to growth of the energy of the neutrinos taken then from the fluid, as you can see here in the black curve. And then if you don't treat all of the relativistic terms properly, you might get something like the green curve, where they're not moving at the right velocity. So doing the proper treatment of the implicit source terms in these moment schemes is important in order to capture these high scattering regions properly, at least. And maybe in other regimes as well, but this is the one configuration where it has been shown to have a large impact. Okay, so that's the two moment scheme. So they are going to be very good if treated properly in the high density regions, but possibly less reliable in the lower density regions where the closure is an issue, and in the semi-transparent regime. The only alternative that has really been used so far that does transport is Monte-Carlo methods. That's something that we've implemented in our spec code for merger simulations, and also been used in the context of post-merger disks by the Los Alamos group in MHD radiation simulations in 3D, and for longer simulations in 2D by the AEI group. So the general idea here for Monte Carlo transport is that effectively you discretize your distribution function as a sum of packets, each representing a large number of neutrinos. And effectively each of these packets is a Dirac delta in phase space. And so this is kind of the representation of your distribution function in Monte Carlo. Conceptually, Monte Carlo methods are fairly simple. The general idea is in each cell you are going to create packets according to the known emissivity of neutrinos. Then you sample the time to the next interaction from the known distribution of from the known opacities of neutrinos to matter, of matter to neutrinos, sorry. And then you propagate your packets along geodesic to that next interaction, and then you process that next interaction. You absorb the packet, or you scatter it, or whatever is needed, right? So the general idea is very simple. The problem is that this works very well in low density regions, but this is both expansive and unstable in high density regions. So this is kind of the opposite configuration from the moment scheme, is that here Monte Carlo methods are going to be potentially problematic in very high density regions, but much better at capturing the behavior of neutrinos in low density regions. So the advantage of Monte Carlo methods is first that they are known to be very efficient at capturing inhomogeneous distribution in a high dimensional space, at least at low resolution. And that's exactly what we are trying to do here for radiation transport of neutrinos. An example of this is shown here. So here I'm showing you the number of packets per unit volume. Again, on a vertical slice to a merger remnant for different types of neutrinos. And this is a log scale. And you can see that most of the packets are in those region close to the surface of the neutron star where most neutrino matter interactions happen. And so packets are distributed, kind of where we need them. And you have adaptivity in exactly how you set where the packets are going to be created and absorbed. They are going to be very cheap and accurate transport methods for black hole plus disk systems because there are no high density regions in these systems. If you have no neutron stars, you get rid of the regions where the Monte Carlo methods are inaccurate. So they are definitely going to be very good at black hole plus disk simulations. And they have flexibility in how you distribute your resources. But as I'll discuss in a minute, you need to play tricks in the high density regions to get them to behave properly. And they converge very slowly. They only converge like 1 over the square root of the number of packets, which means that as we get to higher and higher accuracy simulations, Monte Carlo methods are nearly certainly going to be eventually beaten by even fully discretized transport, let's say, once we have the resources to do something like that, which at the moment no one can do. Plus, of course, Monte Carlo methods introduce noise in your simulations, which can be an issue. We'll discuss that a bit in a minute. Okay, so what do we need to do in the high density regions with Monte Carlo, and why could it be a problem? Well, the first thing is that if you have a high scattering capacity, so if your grid cell is optically thick to scattering, in theory, we have a lot of scattering events in each time step, which is computationally expensive to treat. And the way we handle that is by effectively saying that if we have a high scattering capacity, we can treat one time step as neutrino sampling the outcome of a diffusion of the evolution of a diffusion equation. And this works actually pretty well. Here's an example, for example, for how much neutrino travel over a certain amount of time in a grid cell, both using scattering done, scattering by scattering, which is the black curve, or by solving a diffusion equation, which is the red curve. This is for an optical depth of only 3, so relatively low optical depth overall. And we already see a pretty good agreement between the two methods. And it only gets better at higher optical depth. One of the issues here, conceptually at least, is that the diffusion equation is not covariant. And so we could worry about using it in a generalistic code. We generally use it over a relatively small region where we solve the equations in the orthonormal in an orthonormal tetrad in the fluid frame, and the metric does not change very much over the region over which neutrinos are diffusing over one time step. So I think at the moment this is a very subdominant source of errors in our simulations, but that's a reasonable thing to worry about as we use this kind of method. For the implicit Monte Carlo, on the other hand, so for the treatment of high absorption regions, the main issue here is that rapid emission and absorption of neutrinos can lead to rapid evolution of the electron fraction and temperature of your fluid. and that can lead to numerical instabilities in your evolutions. The main method that's been proposed to avoid that is implicit Monte-Carlo, which was proposed by Fleck and Cummings in the context of photon transport in the 70s. And the general idea here is that you are going to reduce your emission and absorption so that the time scale for absorption of neutrinos in your system is larger than a time step. And you change both of them with the same factor so that the equilibrium energy density, which is the ratio of these two quantities, remain the same. At the same time, you are going to appropriately increase the scattering opacity of neutrinos so that the diffusion timescale of neutrinos remains the same. In the context of photon transport, and for specific choice of that rescaling, Fleck and Cummings have shown that this is just a different discretization of the evolution equations. But this is not quite true for neutrino transport because we couple to both temperature and electron fraction. And in addition, in all major simulations, at least, we don't use the same rescaling for all energy beams and all neutrino species, and that might also be a source of inaccuracies. And so this could be a potential source of error in the treatment of dense regions in merger simulations right now in Monte-Carlo. In the test that we have done, for example, here measuring the luminosity of neutrinos in a 1D line through a merger remnant, we see sub-percent errors due to this effect, but that's over a relatively short time scale. Maybe the main one is, how does that affect the evolution of the system over a long time scale? The truth is that at this point, we do not know for sure. So this is a potential source of uncertainty. Okay, and then the kind of last thing we might worry about for Monte Carlo is the impact of just limited number of packets and shot noise in the simulations. You can see that we do see Monte Carlo noise in these simulations. If we look at the right quantities, the quantity that is most visibly impacted by Monte Carlo noise is the electron fraction, shown here again on the vertical slice. In a simulation with 40 million packets per species and 100 million packets per species. And you can clearly see that the electron fraction in the regions where neutrino-matter interactions are important can be very noisy due to those Monte Carlo packets. And then as you get farther away from the remnant and neutrinos and matter has interacted with more packets and those things kind of average out, you get a smoother distribution farther out. As you increase the resolution, however, the noise does decrease in roughly the way you would expect. And also, maybe more importantly, the average values of, for example, the composition of the outflows does not change much, at least much less than other source of errors that we have in our simulations. And so this gives us confidence that for many of the global quantities, at least that we have in our simulations, Monte Carlo shot noise is not the dominant source of error. The one important exception to this is the amount of mass ejected by the merger. And this is shown in some way here on the left. This is the distribution of the matter as a function of its Lorentz factor at infinity, estimated in the simulation. And basically, everything above 1 here should be unbound. And the farther you go to the right, the faster the ejecta is. I showed 3 plots here. One of them is a 2-moment simulation, which is the green curve. One of them is the Monte Carlo with high number of packets, so the same as this simulation here on the right, which is the black curve. And then the red curve is the one with less packets. And you can clearly see that there's a higher number, there's higher ejected mass in the lower accuracy Monte Carlo simulation. It's about 10% higher mass, which is comparable to expected numerical errors for this simulation. And so here, the effect of neutrino sampling noise, of Monte Carlo sampling noise is comparable at least to numerical errors in the simulation. And of course, ejected mass is an important quantity for us to model, so this is not a negligible source of error. Okay, we have looked at other, because Monte Carlo methods are good in one regime, the semi-transparent and low-density regions, and 2-moment schemes are good in a different regime, which is the high-density regions. By comparing them, we can actually get an idea of how good our current neutral transport methods are, at least at the order of magnitude level, right? Because they are expected to have very different sources of error. And of course, another difference between the two is that the Monte Carlo method is energy dependent intrinsically, while the 2-moment schemes we are using are gray, do not have energy dependence. So that could be another issue with the two-moment scheme. So we have done a number of simulations now where we have run both the 2-moment scheme and the Monte Carlo scheme. In most of them, for global quantities, we tend to see errors of the order of 10-20% between the two transport scheme, which is significant if you think about detailed modeling of matter outflows, for example. But I would argue not at the moment the dominant source of errors in our simulations compared to both numerical error, finite resolution errors and missing physics error. There are a few more detailed aspects of the simulations where we see larger differences. One of them is shown here on the left, where you can see the evolution of the densest points in a metastable neutron star, one that collapsed on 5 to 10 millisecond time scale, where here the Monte-Carlo simulation collapsed on 4 millisecond time after merger, and the M1 simulation, if you continue, collapsed on about 8 milliseconds after merger. So that can seem like a fairly large difference. The truth is that people have seen similar difference by just changing the numerical resolution of the simulations. So this is not overly surprising, but still indicates that there can be an impact of the Monte Carlo scheme, even on the global evolution of the high density region of the merger remnant. If you look in more details at, again, the two-moment scheme at the top using, these are not David simulations, these are spec simulations using David's M1 scheme that we re-implemented in spec. So these are all spec simulations, but using the best current two-moment scheme, which is the one from David, and our best Monte Carlo simulation with high number of packets. You can see that the density looks fairly similar. They are not at the exact same phase in their evolution, so there are slight differences. But qualitatively, density and temperature look typically fairly similar. The electron fraction, on the other hand, can be a bit different between the two-moment schemes and the Monte Carlo scheme. Specifically, we tend to note that the two-moment scheme predict a higher electron fraction in the outflows than the Monte Carlo scheme. You can see that in the polar regions here. And then if we look at the properties of the neutrino escaping your system, if we look at the luminosity of different types of neutrinos, which are the different plots I've seen on the left, now there's a lot of curves here, but the two best scheme for the M1 and MC schemes are the dashed curve for M1 and this dot dash curve for the MC. And they tend to be at least qualitatively in fairly good agreement. Also, there are again difference at the level of 20% in the peak of the emission. You might note this large bump here. This is one of the old M1 scheme simulation, which clearly has something that is inaccurate and unphysical compared to all of the other simulations. But the better M1 scheme and the recent Monte Carlo simulations are at least qualitatively in good agreement for the global quantities. But if you look at the angular distribution of neutrinos, on the other hand, this is polar angle. So 1 is cos theta equal 1 is polar regions, 0 is equatorial regions. All of those thick curves are the M1 results, where you can see a lot of neutrinos in the polar regions. If you do the same simulation with MC, you find a much flatter distribution. And we believe that this is due to the pressure closure used in the two-moment scheme, which tends to keep your neutrinos in that polar region as they interact with each other in ways that they should not. But I'm not quite sure when I started, so how much time do I have left?
You have 7 minutes before questions.
Okay, thank you. Okay. So for the rest of the talk, then I want. Okay, so we have seen like the comparison between the kind of two main state-of-the-art transport scheme, right? The two-moment scheme and the Monte Carlo scheme, and we have an idea now of how they compare with each other, and maybe that's a good estimate of the errors done in the transport scheme. And I think what this shows right now is that qualitatively they are in pretty good agreement, and I think that a number of simulations that have explored the effect of missing physics in simulations are now seeing larger effects than these differences between transport scheme. And that's what I wanted to emphasize now, is that missing physics might be more important now than these transport issues. At least if we use state-of-the-art transport. So these can include things like proper treatment of pairs, muon charge current reactions, inelastic scattering, flavor conversion, and possibly accurate calculation of the reaction rates. The tabulated rates that we get are themselves approximations, and more accurate calculations here, including, for example, many-body effects in the high-density matter could be important as well. One of the most dramatic effects that has been shown was shown by Haringer and Luciano Razzola's group, showing the difference between evolving with muon charge current reactions and without muon charge current reactions. And to include muon charge current reactions, you also need to go from evolving 3 neutrino species, electron neutrinos, antineutrinos, and heavies, to 5 neutrino species where you split your heavies into muon neutrinos, muon antineutrinos, and then all of the tau neutrinos and antineutrinos together. And what is shown here are horizontal slides through the merger remnant at the bottom, vertical slides through the merger remnant at the top, at different time in the simulation. And the colors are the proton fraction, sorry, in this case, which is not the same as the electron fraction in this simulation. And you can clearly see, especially at late time, that the proton fraction is very different in the 3 neutrino simulation than in their 5 neutrino simulations, indicating, and especially it is much more neutron rich in the simulation, including muon charge current reaction. And this is in part because part of the interactions that would have been emitting electron neutrinos and antineutrinos, which can easily interact with the outflows, instead emit muon neutrinos and antineutrinos instead, which do not interact as much with the outflows. And so you can see here a clear effect of these muon charge current reactions. And if you compare these plots to what I showed you for the difference between 2 moments and Monte-Carlo, clearly the difference here is larger. But these are basically the only simulations that self-consistently include muon charge current reactions with an evolution of the muon fraction out of equilibrium, which is important to get these effects. Another important aspect, which David already partially covered, and actually this plot was also in David's talk, is flavor conversion. It comes from David's simulation. So, the general idea here is that we know that if flavor conversions due to the instabilities that happen in the merger context maximally transform neutrinos from one flavor to the other, then it's going to definitely have an impact on the composition of the outflows. This was shown both by Lee and Siegel here on the left, and then in Xiu et al. In David's group here Lee and Siegel on the right and Xiu on the left. Where you can see the composition of the outflows for different treatment of flavor conversions, indicating that clearly flavor transformation can play an important role in setting the composition of matter outflows. But at this point, evolving the quantum kinetic equations, we would have to do this properly. We would have to evolve the density matrix representing the neutrino flavors, and that's already a complication. But on top of that, we would have to include interaction terms that lead to flavor transformation on very short time scales, possibly nanosecond time scales. And that's much shorter than a time step. And so that creates another problem if you want to include these in simulations. So right now we cannot do that. We only have subgrid models that are based on local simulations of these flavor transformations. And the results still depend on exactly how we treat these flavor conversions, as David already mentioned. But this is definitely a potentially important effect to include in the future. Inelastic scattering is not as studied. We have tried to implement in our Monte-Carlo code now a first attempt at inelastic scattering with very approximate methods. I can get more into details later on. But what we find so far is that it does have a significant effect, for example, on the spectrum of heavy lepton neutrinos. So here you see the energy spectrum of those neutrinos with inelastic scattering and without inelastic scattering, and there's clearly a significant difference. And over a longer term evolution, we do, as a result, also see a difference, a significant difference, about a factor of 2 in the amount of matter being ejected over a long time scale in these simulations. Now, this is a configuration that kind of maximizes, again, the potential impact of inelastic scattering, because we don't include magnetically driven winds. And we include inelastic scattering in an approximate manner that probably overestimates slightly their effect. But it also shows that inelastic scattering could also have an impact on the evolution of these systems. Now, one of the issues here is that to calculate some of those reaction rates, we actually would need to know the distribution function of neutrino F nu. But moment schemes only evolve moments of F nu and not enough there's not enough information in the moments to reconstruct the reaction rates, especially for things like pair processes, inelastic scattering, flavor conversion. For all of these reactions, we do not have enough information in the moment scheme to really know what's going to happen in terms of interaction rates. And that's particularly problematic. That's particularly problematic for heavy lepton neutrinos, which are very significantly impacted by these by inelastic scattering, for example, and pair production. And so that's one issue for the moment scheme. In Monte-Carlo methods, in theory, we have at our disposal the distribution function of neutrinos, but in practice, this is not quite the case. And for example, if you make an estimate of what the energy of a packet in current Monte-Carlo simulation is, you will find that it's about 10 to the minus 10 to 12 m sun c square. But the energy of, if you had one packet that would create a distribution, an F nu of 1, which is the maximum value for a fermion, the energy of that packet should be of the order of 10 to the minus 13 times some scaling with the energy, but something that is of order 1 for 20 MeV neutrinos. And so we know that in our simulation, a single packet can get you from F nu of 0 to F nu of 100 pretty easily, which of course does not allow you then to reconstruct the distribution function of neutrinos reliably at a single time in the simulation. Now, the reason Monte-Carlo works in merger simulation is that because in many regions, neutrino matter interactions are relatively slow, and so we actually average over many interactions with packets over a relatively long time scale compared to our time step these interaction rates, and that's why they give good results. But if you try to get the distribution function at a specific time, this is highly inaccurate at this point. So we'd have to figure out a way around that in Monte Carlo if you want to actually use detailed calculation of reaction rates. Right. So that's roughly where we are right now. We have state-of-the-art transport algorithms, two-moment schemes, Monte Carlo methods that provide predictions for the global quantities that seems to be reliable with the 10-20% level, roughly speaking, but do differ in their predictions for more detailed quantities like the spatial distribution of neutrinos and outflows, and do still have a non-negligible impact on things like the composition of the outflows. On the other hand, beyond this transport scheme, we see that missing physics in the simulations is a very important and largely unquantified source of error for us. And here I would include certainly muons, flavor conversions. I didn't talk much about pair processes, but pair annihilation in the polar region is also very inaccurately modeled at this point. Inelastic scattering, potentially many-body corrections in the calculation of the interaction rates. All of these could be important. And it's not just about adding these interaction rates in our tables, because for many of these processes, we do not have enough information in our current transport algorithm to actually calculate these interaction rates with high accuracy. And so that is a limiting factor at this point in our simulations. I'll stop here, and I'm happy to take any questions that you might have.
Thank you very much for the very nice talk.